All right, so the direct substitution ones, these are the easiest limits. These are the limits where you can just take the value and plug it in for x or for whatever variable. The bottom ones in that case would be t. So direct substitution, you should always try it first. Now, you could try it just mentally if you want. You don't actually have to write it out. But always try direct substitution first. And a lot of times, even when direct substitution doesn't work, the result you get will tell you what to do next. It'll tell you if you're going to get a limit, or if you might get a limit and you have to try something else to get it. It'll tell you sometimes when the limit's just not going to happen. So by trying direct substitution first, it's going to help you out a lot. So this first one here, this limit as x approaches 0 of 2x squared plus 3x minus 4, anytime you have a polynomial, direct substitution is going to work. You can just plug in the value and get your answer. So what would we get here for this first limit? Yeah, we put in 0. That's going to make the first two terms here, this term and this term, go to 0. Those are going to be 0, and we end up with negative 4. That's pretty straightforward, right? How about the second one? What do we do there? Yeah, we're going to plug in 3. So we get 2 times 3 squared plus 3 times 3 minus 4. I'm not going to waste time doing the arithmetic here. You guys can do that, right? So you guys understand how to do that? Does anybody want me to do either of those bottom two? I put more examples than I thought we would need just in case you want more practice with it. You guys want me to do those two or move on? Okay, one person said move on, so we'll move on. I want to talk about one-sided limits. I talked about this earlier. Do you guys see in these limits right here, the little, it almost looks like an exponent, but it's a plus sign or a minus sign? What that means is, in this case, x is approaching 0, but it's not approaching 0 from both sides, it's approaching 0 from one side. Which side is it coming at 0 from? From the right. Okay, so if we're looking at the limit as x approaches 0 from the right of f of x, we're looking at what happens to this function as we get close to 0 from the right, and what are we going to get? 0. Okay, how about the next one? X approaches 3 from the left. What are we going to get? What's the value of the function? 3. Good. How about as x approaches 5? Now, this doesn't have a one-sided limit, so what do we have to make sure of? It's the same on both sides. Is it the same on both sides? Yeah, it's the same on both sides, which is what? 1. Okay, good. By the way, the grapher that I used, I put the open holes here. The graph shows that it's going through it, but that isn't. It's a hole in the graph. I think you guys can figure that out, right? How about 7 from the left? What value is this function approaching? Okay, how about 7 from the right? Okay, so how about 7? It does not exist. So you could just write for something like that, does not exist, DNE. Okay, and it doesn't exist here because from the right and from the left it approaches different values. How about 9 from the left? 1. How about 9 from the right? 1. So how about 9? So does it matter here that the value of the function at 9 is actually 4? No. When we're talking about limits, the value of the function at that point is irrelevant. It doesn't matter. So even though the value of the function at 9 is 4, the function itself is approaching 9, or is approaching 1 as we approach 9 on the x-axis. Does that make sense? Okay. So this is an important definition. Don't write it down now. If you want to write it down, it's in your book. But it basically says that the limit of a function is L, some number, if and only if, you guys know the double arrow, what that means? If and only if the limit as we approach from the right is L and as we approach from the left is L. So if the function approaches the same value from both sides, then the limit exists and it's equal to L. If it approaches from different sides, if it approaches different values from both sides, then it doesn't exist. Does that make sense? Okay, moving on. Analytic manipulation. We did a problem like this yesterday. We actually just looked at it here. This first problem, if we try direct substitution, what are we going to get? We end up with, not necessarily undefined, but we get 0 over 0, right? 0 over 0, we don't know what that is. If you guys remember the first day of school, I told you I'm going to teach you how to learn. I'm going to teach you how to learn. I'm going to teach you how to divide by 0, but only when we divide 0 by 0. So we don't know what 0 divided by 0 is, so we're going to have to try something else. The direct substitution is not going to work. What do you think we could do here? Abdallah? What's that? Yeah, we could factor out an x on the top. So this is going to equal the limit as x approaches 0, don't forget that, of x times 3x plus 2 over x. That's not an x. Okay, so all we did is factor it, and now what do you notice? We can cancel out the x's. Now, normally we couldn't do that because we would have to worry about canceling out a 0, wouldn't we? Do we have to worry about that here? Why not? Could x equal 0 in this problem? No, we're not looking at the values when x equals 0. We're looking at the values around 0, surrounding 0. So x is not equal to 0. It's just close to 0, which is okay. We can divide by numbers close to 0 and not have any problems with it. So this is the same thing as saying the limit as x approaches 0 of 3x plus 2. Now can I use direct substitution? Yes. I could just plug in 0 here. We can see here that this term here is going to go to 0. It's going to become 0 because 3 times 0 is 0. And what do we end up with? Yeah, 0 plus 2, which is 2. Does that make sense? I'm not going to do this example. I think you guys know how to do it. But what would we do first? Factor the top. We would get t plus 3, t minus 2. Then we can cancel out the t minus 2's because we know t doesn't equal 2. It's just close to 2. And then we can plug in the 2 into what's left and get our value there. Okay, so sometimes if we try direct substitution and we get 0 divided by 0, we can manipulate it in a way that we can plug it in. We can use direct substitution. We just have to cancel something out first. We have to cancel those zeros out. Does that make sense? Okay, moving on. If you were to write something like this on a test, and I'm going to give you a lot of information about how the tests went. I'm about halfway through the second part right now. Along with giving the test back, I'm going to give a note sheet about things that you guys need to get better with next time. Notation is really important. So when we're dealing with limits, it's important to understand what's proper and what's not. Because if you write something that's wrong, then you will lose credit for it on the AP test. Okay, even if it's something that you know in your mind that, well, I didn't actually mean that, I meant something else, then you need to write that something else, write what you actually meant. The problem with this is right here. It is not true that x times 3x plus 2 over x is equal to 3x plus 2. They're not equal to each other. Like I said on the previous problem, sometimes they are. Usually they're equal to each other. When are they not equal to each other? When x equals 0. So if you write an equal sign like this, it's wrong. And anything you do after that is based on something that's wrong, and you may get a wrong answer. And even if you get the right answer, you may not get credit for it. You know, that sounds silly, but you need to be able to get to the right answer the right way. So instead of writing it like this, we need to be sure we keep that limit on there to show that we're not dealing with the value at 0, but values around 0. And that's what that limit does for us. So we need to be sure we keep that limit on there until we can plug it in, until we can use direct substitution. And then once we plug it in, which is at this step right here, we put 0 in for x. Once we plug it in, we can get rid of the limit. So we need to be sure we keep that limit out front until we plug it in. Does that make sense? Keep that in mind when you're doing these problems. Okay, let's try direct substitution on these. What do we get here if we plug in 0? Try direct substitution. 3x squared is going to become 0, so we have 0 plus 2 on top over 0. So what we have is 2 divided by 0. Now, in a previous problem, we got something divided by 0, and we did some analytic manipulation. We factored and we canceled something out so that we could plug the number in and not divide by 0. Do you think that would work here? Do you think analytic manipulation would work here? I heard a no. Why not?
Because there's no proper way to factor it.
Okay, so looking at the problem, you can see there's no way to factor it, and so we won't be able to do it. But just looking at what we got when we substituted, based on this right here, 2 divided by 0, what tells me that I'm not going to be able to cancel anything out that would help? That would be helpful. Cole?
2.
Yeah. When you get 0 divided by 0, you might be able to do something. 2 divided by 0, you're not going to be able to do anything, ever. If you have a number on top and a 0 on the bottom, let me clarify that. If you have a number that's not 0 on top and 0 on the bottom, you're not going to be able to do it. So even if you were to cancel something out, you're not going to be canceling zeros out, and so you're not going to get rid of the 0 in the denominator. So what this tells me is the limit doesn't exist. If you get something like 2 divided by 0, the limit doesn't exist. Okay, does that make sense? If we look at this second one here, we can just see here theta is approaching pi. So what are we going to get on top? What are we going to get on top? Oh, this is a bad problem, isn't it? That's supposed to be pi divided by 2. There we go. Now it's a good problem. So what do we get on top? Pi squared over 4. What do we get on the bottom?
0.
What is cosine of pi over 2? 0, right? Because cosine starts at 1 and then at pi over 2 it's at 0. So what we end up with is pi squared over 4 divided by 0. Again, we get a number divided by 0. It doesn't exist. So we would just say does not exist. Quick note on does not exist. Don't write does not exist when you actually mean something else. So does not exist has a very specific meaning. Particularly with limits, it means that the limit is approaching either different values from both sides or it's approaching an infinite value, but it doesn't really have a meaning in other areas. So don't write does not exist when you really mean to say there's no solution, or what would be another one that somebody would use it for? Don't know how to do it, or you can't do it. If it's a problem that you can't do by methods that we know, you wouldn't say it doesn't exist. You would say that you can't do it, or however you would say that. Okay, did anybody look at this in the book? Sandwich theorem. It's in section 2.1. You guys didn't really explore much, did you? Just kind of did what I told you to and stopped. Yeah. Okay. The sandwich theorem is actually really cool. It helps us find limits that we can't really find in other ways. So we want to find the limit of this right here, the limit of x squared times sine of 1 over x as x approaches 0. If you try to plug this in your calculator, you're going to run into a problem when? At what point do you get a problem here? Cole?
The sine of 1 over 0.
Yeah, because we have a 1 over 0, right? And the sine of 1 over 0 is, well, we don't know because you can't divide by 0. So what we're going to do here is we're going to use a property of the sine function. Mostly that the sine function we know is always going to be between -1 and 1, right? Sine can never be less than -1. It can never be greater than +1. You guys agree with that? Okay, so what we're going to do here is we're going to squeeze this function in between two other things. I know that the sine of 1 over x is always between -1 and 1. All right, so if I multiply everything here by x squared, and x squared is always going to be what? Positive or negative? Or could it be either? Could x squared be negative? No, we would be worried here if x squared could be negative and we multiply by a negative, then it's going to flip our inequalities, right? But we don't have to worry about that here because x squared is always positive. So we're going to multiply everything by x squared, and I'm going to cheat here. I'm just going to use what's already here. So we have x squared times negative 1, x squared times the sine of 1 over x, and x squared times 1. This inequality is still going to be true. X squared times the sine of 1 over x is always going to be between, and let's simplify this here, x squared times negative 1 is just negative x squared, right? So it's always going to be between negative x squared and positive x squared. Do you guys understand how I got that? Now here's the cool thing about that. What is the limit as x approaches 0 of negative x squared?
0.
0. Just plug it in, right? What is the limit as x approaches 0 of positive x squared? 0. Just plug it in. All right, so I know that this function, x squared times the sine of 1 over x, is always between negative x squared and positive x squared. I also know that as x approaches 0, this goes to 0 and this goes to 0. So what's going to happen to this? It has to stay between them, and if they're both 0, then it has to be 0. Okay, now when I say between, it can also be equal to them, right? So that means that this limit here is 0. Does that make sense? Here's a picture of what's happening. So the red function is x squared. The blue function is negative x squared. The function x squared times the sine of 1 over x is in green. And you can see that it always stays between the blue function and the red function. But since they're squeezing together at 0, then the green function, x squared sine of 1 over x, has to stay between them. And even though it's not defined at 0, the values around it have to be really close to 0 because they're being squeezed between negative x squared and positive x squared. Isn't that fun?
It's crazy.
Depends on your definition of fun, I guess. I think it's fun. Okay, working with infinity. These are, first of all, I need to clarify here, you cannot treat infinity as a number. Infinity is a concept. I talked about that on the first day of school. However, you can use infinity in a way like a number. If you understand the concept of infinity, you can understand what's going to happen when we start multiplying, dividing, adding, subtracting infinity. So I've got a few things here. I got 6 of them here. I want to know if I have a number, any number, that's k, that's a constant, and try to divide that number by infinity, which the idea of infinity is a really big number, right? So if I take k and divide it by a really big number, what's it going to get close to?
0.
It's going to get close to 0. We take any constant, divide it by infinity, and we're going to get 0. Now, just to be clear, so you don't go home and say, okay, Mr. Betts said that I can divide by infinity. What I'm actually asking is, what is the limit as x approaches infinity of k divided by x? So as x gets bigger and bigger, what's the value of this fraction going to equal? That's what I'm actually asking here. I'm just writing it in a simpler way because we're going to want to know what happens when we divide by infinity, multiply by infinity, and so on. All right? Okay, moving on. What if I take some positive constant and divide by negative infinity? A really big number, but a negative really big number.
0.
Excuse me. Yeah, it's still going to be 0. Okay. What if I take a really big number? Okay, what about a really big number divided by a constant? A really big number. We'll call it infinity. What about a negative really big number divided by a constant? A negative. Now the assumption here is that k is positive, right? If k was negative, then these two would be flipped. So if we would have a really big number divided by some negative constant, then it would be negative infinity. If we had negative infinity divided by some negative constant, then it would be positive infinity. Does that make sense? Okay, and again, infinity isn't really a number. It's an idea. It's the idea of an unbounded number, as big as you want it to be. Okay? So what if we take some infinite number, some unbounded function, and divide it by some unbounded function? No. We don't know. It could be infinity, it could be 0, it could be some constant, it could be just unknown. We don't know. It's called an indeterminate fraction in this case. So we don't know what it is. This would be a situation kind of like when we had 0 divided by 0. We don't know what it is. We have to do something else. Okay? Same thing here. I think you could tell where we're going with that. We don't know what that is either. Okay? It could be infinity. It could be 0. It could be anywhere in between. Okay? I know it says working with infinity here, but we're going to be dealing with 0 and infinity quite a bit. They're very closely related to each other. What if we have 0 divided by some positive constant? 0. What if we have 0 divided by some negative constant? Okay, those are easy. What if we have some positive constant divided by 0? Yeah, it's undefined. I'm going to say we don't know. Because it could actually, it could be undefined. It could be infinite. And there's a subtle difference there. So I'm going to put a question mark for now. We'll get to those differences later. A negative constant divided by 0? Still don't know. 0 divided by 0? Don't know. We already talked about that. We don't know that one either. That's indeterminate. All right? Now, here's where we start talking about those subtle differences. What if we have a positive constant and divide by a number that's just barely bigger than 0? So we're dividing by a really, 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 really small number, but it's not quite 0. So it's not undefined. What's that? A really big number. If you divide by a really small number, you get a really big number. We'll call that really big number infinity. If you take a negative constant and divide by a really, really small number, so a number really close to 0, so do you guys understand what I mean by this? This is the same notation we use with one-sided limits. I will call this positive 0. So we're going to treat 0 as if it could be positive or negative. So if we take a number really close to 0, but just a little bit bigger, divide it into a negative constant, what are we going to get? Negative infinity. So the negatives, the rules with negatives and positives are the same as we have when we're just multiplying and dividing integers. So we would have a constant divided by negative 0, or a number just barely less than 0 would be a really big negative number, and a negative constant divided by negative 0 would give us a really big positive number. Does that all make sense? Now again, what we're really talking about here is limits. We're talking about the limit as x approaches 0 on the bottom, but we want to be able to think about it in simple terms like this. Okay, so we have two things we want to talk about: horizontal asymptotes and vertical asymptotes. Before I give you the rest of the day, and I know I'm going longer than I planned. I always do. You'll figure that out. With those ideas we just talked about, we can use direct substitution in infinite limits. Okay, or at least we can use the idea of direct substitution. So what we have going on here is we have 4 minus 1 over x squared, and x is getting really, 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 really big. So if we plugged in a really, 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 really big number here, the number in the denominator is being squared, so not only is it really, 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 really big, but it's a really big number being squared. So if we have 1 over a really big number squared, what are we going to get? 0. So we can use this idea of direct substitution with infinity and kind of treat infinity as a number, as long as you understand what's going on there. So we're going to get 4 minus 0 here, and that limit's just going to be 4. Does that make sense? Okay. What if, instead of a really, really big number that's positive, we put in a really, really big number that's negative? Well, this problem's convenient because, why? Yeah, the squared means it's really exactly the same thing as this one, right? Because as soon as we take the negative number and square it, it becomes the positive number squared also. So what's going to happen here? 4 minus 0, which is, yeah. So we're going to have 1 divided by infinity. And if you wanted to write that, technically this doesn't have any meaning. You can't really do 1 divided by infinity. But the idea is we're divided by a really big number. That's going to be 0. And so 4 minus 0 is 4. Okay? Now, this actually tells us something really important. If you were to look at this function on a graph, if you were to graph 4 minus 1 over x squared, in the middle of the graph, it's going to be doing some interesting stuff. But as you move to really big positive x values and really big negative x values, the graph is going to get closer and closer to a value. As x gets really big, the values of the function get really close to 4. And as the x values get really small, or really big in the negative direction, the value of the function is going to get close to 4. So what that means is this function has a horizontal asymptote. And I thought I put a picture in there, but clearly I didn't. So this function, I don't know exactly what the function looks like in the middle, but if I were to graph it, and I'm going to put a horizontal asymptote here at 4, I do know that the function is going to be approaching 4. We could also look at this more closely and say, okay, well, this is going to 0, but it's a negative 0 because we're subtracting, right? So we're looking at numbers that are just a little bit less than 4. So we know that the function is going to look something like this and something like this as it goes off to the sides. The middle is yet to be determined. We don't know what's going on in there. Okay? Questions about that? Does that kind of make sense? Kind of make sense? Sort of? Okay. We saw this limit earlier, didn't we? Except it wasn't one-sided limits. At the time, it was just an overall limit. And we said we got 2 over 0, so it doesn't exist. So let's look at it from one side and the other. All right, as x approaches 0 from the left, here's where it gets a little tricky. Sometimes a really, really, really small number, it doesn't matter if it's coming from the left or the right, nothing's going to be different about it. And that's the case here with the x squared. Does it matter if I'm dealing with a number a little bit left or a little bit to the right of? No. All right, so there it doesn't matter. So again, let's try direct substitution, but let's use some of the stuff that we know. So we're going to have, what's this first term going to be here when I put 0 in? 0, right? So we're going to have 3 times 0 squared, which is just 0. So we have 0 plus 2 on top. On the bottom, we're going to have 0. But since we're approaching from the left, we have a negative 0. And here it does matter. So what we have, and this is one of those properties that we looked at, we have a positive constant divided by a negative 0. What's that going to give us? Negative infinity. So we have a positive number divided by a number that's really close to 0, a really small number. So it's going to be a really big number, but since that small number is negative, then we're going to get negative infinity. So the answer to a limit problem can be infinity or negative infinity. All right, so as this function approaches from the left, it's going to approach negative infinity, which means that the values get really, really, really big, but in the negative direction. If we use direct substitution here, we get 0 plus 2 over positive 0, which is just 2 over positive 0. And what's that going to be? It's going to be positive infinity. So that means that as this function approaches from the right of 0, it's going to go to positive infinity. What do you think this means as far as what the graph looks like? The graph of this function. So we're looking at this function around the values of 0. We know that the values are going to negative infinity on the left and positive infinity on the right. So what's the graph going to look like around 0? Exactly. It's going to be an asymptote, and it's going to look like that. Here's the picture that I thought I put up there. So as we approach from the left, you can see it here. As we come in from the left, sorry, let me do something here. Okay, as we come in from the left, the values go down to negative infinity, which is what we got from our limit, right? As we approach from the right, the numbers to the right of 0, it goes up to positive infinity. Okay, so we get asymptotic behavior when we have infinite limits. So if we have a limit that approaches infinity, we're going to end up with asymptotes. Okay? I don't know how you guys have defined asymptotes in your past math classes, but technically to define asymptotes, you have to use limits. So you've kind of talked about what they mean, but we actually use limits to define asymptotes. So vertical asymptotes happen when the limit from either side of a value of x approaches infinity or negative infinity. Does that make sense? So we get horizontal asymptotes when we look at what happens when x approaches infinity. We get vertical asymptotes when we look at what happens when x approaches some constant and we get an infinite limit. Lots of information there. Okay, here's what you need to know how to do. This is not everything that you need to do, but here's what you need to know how to do after today, after what we talked about today.